Sir, we are live, sir. Please start.
Okay, let me share my screen. Okay. I hope the slides are visible. Okay, thank you. So, hello, good evening, everyone. Thanks a lot for joining this session, which is the collaboration between ANSYS and NPTEL. We are starting with our first session on the electrification, which is the robust and efficient electric machine development through simulation. Before we start, let me introduce myself. My name is Tushar Sambharam. I'm the principal technology specialist at ANSYS. I've been working with ANSYS for about more than 16 years, predominantly working in the domain of the electromagnetics, low frequency electromagnetics, talking in terms of electrical machine transformers, the power electronics, and so on and so forth. I have worked with several automotive OEMs across the globe in developing the simulation related workflows in their product development and validation technologies. And today I'll be talking about the electric machine development through simulation with a more context, of course, with automotive and what are the challenges that the automotive industry sees as of now in terms of developing these electrical machines. So let me get started. But before we go, let me, as I am representing ANSYS, let me quickly introduce ANSYS in about less than a minute. Now, many of you must have already used ANSYS in your academics. So ANSYS started off as a mechanical FEA simulation software provider, but over the years, we developed the technologies that are parallel, adjacent to what we were doing, at the same time adding value in terms of what we can offer to our customers or the research associates that are engaged with ANSYS. With that in mind, we kind of developed a simulation ecosystem that caters to almost every needs of product development. So we are not just talking about doing some kind of simulation to cater some specific problem, but we are talking about how to make the overall product development itself efficient, fast, and cost effective. So be it from the physics point of view, the process point of view, the software point of view, or even the data or digital engineering point of view as well, we have developed solutions that cater across this space. And being a simulation provider, I'm here to represent how the simulation-led workflows are getting used across the industry. So I may not be talking specific to ANSYS in my talk, but I'll talk more in terms of the simulation industry, how the simulation-driven workflows are getting adopted across the industry in their product development, specific focus on the electric machines. Now, before we get into the electric machine, let me set the context in terms of electrification itself, right? I don't need to tell this crowd in terms of what is the electrification and why is it important. We already know, everybody knows why electrification is so important and where we are heading with that. But the challenges with electrification compared to the IC engine is electrification is much more complex in terms of the interdisciplinary aspects. It may not be as complex as IC engine if you take just the component point of view in terms of how the combustion works and so on and so forth. But when you look at the interactions that happen inside the electric vehicle between the different components of different physics, it significantly adds in terms of the complexity of how do we go about balancing all these different components. Some are in mechanical nature, some are in electrical in nature, some are just chemical in nature, for example, batteries, so on and so forth. And that adds significant of complexity in terms of how do we come up with a system that behaves perfectly as we want. Then on top of it, there are layers of other aspects. For example, software. We talk about these days, the software on a car is extremely complex. It's not like what we used to have a few years back. We talk about the software defined cars. So software is a big aspect. How do you make sure your products that are going to be on the vehicle work together well with the software? That becomes an essential part of your product development or engineering as a whole. the functional safety, the safety of the vehicle itself is important, and that's stressed out. There is enough significance that has been put by the industry in order to ensure the functional safety of every component that goes into the vehicle. And that's where, again, the safety aspects come into picture. And finally, when you're looking at this kind of complex systems, the system engineering becomes important. So you don't look at the motor. For example, we are talking about traction motor today. You don't look at the traction machine in its isolation, because this machine has to go and fit in a vehicle, and vehicle has its own set of challenges in terms of where I am getting driven, in what ambient conditions it is getting driven, what kind of terrain it has to support. So you don't tunnel down your vision to the component, but you have to go from a system to the component view, and that's where the system engineering comes into picture. And I'll talk about that in my slides. How do we percolate down from a system to the component? And then you have all these different components in your system, which needs to be designed and developed. And each of these components or subsystems have their own challenges in terms of, for example, if I'm designing a battery, I have to see how I can reduce the range by 30%. If I'm designing the motor, I have to see how I can reduce the development time by 2x or 10x. Those kind of challenges are there in every component or every subsystems. And we are going to talk of a lot of these things in the webinar series that we are conducting through this engagement. Today, we'll be focusing more on the motors. We talk about what are the challenges in developing the motors, how do you address those using the simulation, and what is the best methodology that are put forward. So that will be the focus of the today's talk. But of course, other topics are also there in the pipeline, and you will be able to tune in and listen to the other topics in the later on sessions. So coming to the motor specifically, this is the agenda that I'm planning to cover today. We'll talk a little bit about the overview. What is the traction machine? Just to give a context in terms of for non-electrical engineers, about the overall working of the electric machines. We talk about the electric machine design workflow. We talk about simulation for the traction machines. We'll talk about the motor controller and integration of the motor onto the system as well. And then finally, I'll reserve some time towards the end, 10 to 15 minutes for the question and answers that I'll take up. So with that, let me get started with an overview. Let me just in simplicity put what is this. Now, if you talk to any electrical engineers, the electric machines are not new for us, right? We have electric machines have been there from years and years, probably even before the IC engines as well. But the form of the electric machines that we have right now, or we used to have before, to the form of the electric machines that are typically what we are designing for the traction application for the electric vehicles, it's significantly different. And what is changing there? That's the first thing we want to understand, and that will finally percolate down to what are the challenges that we need to address. Okay. First thing about the conventional motors is conventional motors tend to be a little bulky. They tend to be a bit larger. They are not supposed to be placed in any space constraints, right? So they are supposed to be in an industrial atmosphere or anywhere where you have enough premium of the space available. So you could put a larger machines. You don't need to have a huge amount of energy density in these machines. But when you talk about the traction machines, which are going onto the electric vehicle, they need to be very, very concise, because the space is the premium on a vehicle. Every inch of space that you save is significantly valuable compared to what you see in a typical other industries. So that's where the energy density of the electric motors comes into prominence. So when you're designing the motors for the traction applications, you have to pay. You are basically pushing the material, the characteristics of the motor and the performance to the envelope, to the limits, and that's where you need to design it much more stringently when you are designing for traction application. Another thing about the conventional motors is they're typically supposed to operate on a rated speeds plus or minus 5%, let's say, and they're supposed to be operating with a fixed load and fixed speed kind of a condition. But when you put these motors on a vehicle can be operating with 5 people in back or 1 person in the back. It could be operating in a city traffic. It could be operating on a freeway. So you have range of loads and range of speeds that it need to cater. You cannot fix one operating point of the motor. It has to operate across the different envelopes, and that changes the operation significantly. The conventional machines typically are fed from the wall supply, so you probably receive more or less good quality sinusoidal supply for these motors. But when you put an electric vehicle, you have to be fed with the DC and a DC source, which is the battery, and an inverter. So you induce a lot more harmonics into the currents that you inject into the motor. So it needs to work on that as well. And there also the performances can drastically be different, and the design approach also needs to be different. Finally, the motors on the conventional approach are much more rugged. They are placed in a large environment and have much more bigger in size, while the traction machines are delicate. You need to manage them properly and maintain its health much better. So your health management, prognostics, and diagnostics also becomes very important here. Now, one thing I want to put forward beforehand itself is electric machine design is a truly multidisciplinary problem. You cannot have seen in the industry. I've been talking with several people across the industries. When you are designing an electric machine, if you cannot think just as an electrical engineer, you have to wear different hats. So you have to go beyond your kind of a laid down expertise area, because it is a truly multi-physics problem. There is thermal, which is coupled with electromagnetics. There is mechanical noise, which is coupled with electromagnetics. There is a software part, so on and so forth. And all of them, they are connected with each other. So you need to use a multidisciplinary approach. And that's what the industry is doing. We do not have electromagnetic motor design experts anymore. We have the motor design experts who can talk about the electromagnetic design. He can talk about the thermal management. He can talk about the NVH and the motor control as well. So you have to wear different hats. And even if you kind of be a master in one domain, you still need to understand other domains as well to be able to deliver the right kind of a design of electric machines for the required application. So that's one thing I wanted to lay down beforehand itself. Now, coming to the electric machines itself, as I said, electric machines have been around for a long time, and there are different types of machines. There are many initially machines which are stationary field machines, the DC machines, which are, you can say, early generation machines. But right now, what we are mainly dealing with the rotating field machines and the switched machines. In case of rotating field machines, we are mostly engaged with synchronous machines. Asynchronous machines, typically an induction machine. There are few electric vehicles who are exploring the induction machine as well. Some have deployed as well, but more focus has been on the synchronous machines. And in synchronous machines also, we don't have there is a permanent magnet synchronous machine. PM excited synchronous machines are the ones that are mainly being worked on. So most of the vehicles or electric vehicles that we see in the industry, they're kind of focusing mainly on the permanent magnet synchronous machines in different shape and form. But there are a few people who are focusing on switch reluctance or the synchronous reluctance type of topologies as well for the EV application. There are limitations which I'll talk about later, but most of the work is right now on the PM synchronous machines itself. Now, typical constructions of the electrical machines, if you look at, the left side I've seen is basically a typical construction of an induction machine. Most of the times your machine will involve a stator. The stator will have some kind of a winding. What kind of winding, how that needs to be wound is all the design criteria. So you have to come up with that. On the rotor side, there could be the difference. The stator typical layouts look more or less close enough. On the rotor side, depending on what type of machine, you can have different things. If you have an induction machine, you will typically have a rotor laminations, which are made up of a steel. You will have the rotor bars, which are made up of aluminiums, which induce the eddy currents, and that's kind of creates a torque in the motor. That kind of is the source of your torque. These machines work purely on a principle of induction. That is basically the stator field and the rotor field are not really synchronous with each other, but the rotor field is lagging behind the stator field, inducing the eddy currents which are producing the torque. Now, when we come to the permanent magnet machine, instead of rotor bars, you will have the permanent magnets. And again, there also, depending upon where you place the permanent magnet, there are different topologies. There are surface permanent magnet motors where you place the magnets on the surface of the rotor, while the interior permanent magnet machines, where you kind of embed the magnets inside the rotor. You kind of create the slots inside the rotor and insert your magnets in that. And the way you insert those magnets, what kind of a shapes they take, how they look, this is all becomes the IP of your design, because there are n number of shapes that are people are generating these days, and everybody is creating their own kind of IP, their own patents based on that as well. So the arrangement of the permanent magnets as well is also another critical area where people are doing a lot of work in terms of what is the best way to extract the torque out of the motor by arranging these magnets in what fashion will give me the best performance. So the construction also is again it's something that goes through a lot of different variations, but in principle this is what the components will look like. Apart from that, of course, you will have the synchronous reluctance machines or switch reluctance machines, which purely work on a reluctance principle, which doesn't have permanent magnet at all. You try to create a reluctance torque by creating a angle between the stator and rotor magnetic fields, and you try to create a generator torque out of it. The advantage of using a synchronous or switch reluctance machine is you save the cost on the magnets, which is extremely costly for PM machines typically. So there is a lot of work going on in those as well. Now, what should be the attributes? How do I go about designing an electric machine for the traction application, right? Now, typically, when you look at the traction application, you have to follow a typical kind of a torque speed characteristics that we talk about, which I'm showing in the right side image. You have the constant torque region, then you have the constant power region where the torque drops with the speed. And that's the torque speed envelope that you typically refer to as a requirement that you want to have. And that's something that you validate your motor across. And when what this torque speed envelope tells is the different zones of driving. For example, if I am operating at a low torque, low speed condition, that typically indicates where I'm driving in a town condition where there is a lot of traffic, I cannot accelerate too much, so on and so forth. Or the second one, that the high speed and low torque condition tells me I'm on a freeway. I don't need too much torque, but I'm cruising at a higher speed, so I'm just maintaining that speed. So that's a condition. The third one is the hill climb driving, where you need a lot of torque. You don't need too much speed because you are in a hilly region in a terrain where you need to go uphill. So you need to produce a lot of torque, but you may not need a lot of speed to drive the vehicle. And finally, in between region, which is the high torque and high speed region, which is the sport region. So you're kind of accelerating and gaining the speed. So you're kind of driving more with a lot more power than required. So that's a sport driving. So depending upon the driver's condition, where he's driving, how he's driving, he could be driving your motor in any of these regions. He may not be just fixing in one region, right? He could be across the regions he is working on all these things. And that's where the different attributes of your vehicle needs to be validated across using this torque speed envelope. So you need to have high starting torque. You need to have easy speed control. You need to have the good torque speed characteristics. You need to have high energy density because again, the size of the machine is very important. You need to have good efficiency over the overall operating range. For example, I cannot say that I get a range from my battery of over 400 kilometers on a freeway. But if as soon as I being in a city, it just becomes 100 kilometers, that's too much of a variation, right? You need to make sure you balance it across the different drive conditions. So that's again important part. And again, the regeneration, because the motor is not just supposed to operate as a motor, it needs to work as a generator as well. So it needs to give the energy back as well. And regeneration is the another important aspect in that. Now, if we compare different topologies across the different conditions like energy density, efficiency, cost, so on and so forth, this is just my view. Some people may differ in terms of their view of this comparison, but I just wanted to lay down that there are a lot of characteristics across which the PM synchronous machine works much better, of course, in terms of noise, in terms of efficiency, in terms of energy density, so on and so forth. Compared to the other machines, which are induction machines or switch reluctance machines, which are considered for the traction applications. And that's why PM machines are much more preferred. Permanent magnet synchronous machines are much more preferred for the electric vehicle application compared to any other machines. So that's just I wanted to lay down. Of course, there could be a different views. There are people who are very passionately working on switch reluctance machines, and they are improving it, and they are making it viable to for the EV vehicles as well. Even induction machines as well. But of course, right now, what we see in the market is mostly permanent magnet synchronous machine. Okay. With that, let me get down to the second point, the electric machine design workflow. How do you go about designing the electric machine from the traction application? Now, typically, when you start designing for an electric vehicle, you have the vehicle level requirements. I need to know, okay, I'm designing an SUV, I'm designing a sedan, so on and so forth. This much space may be available for me, or this much will be my acceleration needs, this much will be the maximum speed range, so on and so forth. I want my vehicle to run from 0 to 100 kilometers in 10 seconds, so on and so forth. So those are all vehicle level requirements. From there, you come down to a architectural level decision. So you then decide, okay, if I need to meet this vehicle level requirement, I need to go with a specific architecture of the electric vehicle. I need to go with a single motor, dual motor. I want to go with a series or a parallel combination. What kind of battery voltage I want to use, whether I use for 400 volt, 48 volt, or even some people are using 800 volt architectures these days. So those are all different decisions come out from there. Then you go into the powertrain level studies, because now you need to understand, okay, this is all on the vehicle level. I need to understand what is the load that is coming onto my motor from the powertrain performance. So I need to do some kind of a calculation based on the forces that are experienced by my vehicle. So I'll talk about those calculations in a later slide. From there, you derive, okay, what is the requirement from my motor? Okay, my motor needs to deliver this much of continuous torque, this much of peak torque, this much of max speed, so on and so forth. And that becomes your first set of constraints to your design. Now, typically, these three initial studies are done by the OEMs. Then OEM may rely on a supplier to design the motor, or they may design themselves as well. But depending upon what the approach they have, they can go for a in-house design, or they push it to a supplier. There, once you get into the design aspects of the motor, you start with the sizing of the motor, what kind of dimensions it should have. You analyze magnetically, you analyze thermally, you analyze for NVH, you analyze for lifing, and so on and so forth. And finally, once the design is ready, then you talk about, okay, how do I make this motor work with the vehicle? The first thing you need to make sure is make this motor work with the controller. So how does it work with the controller? That's the first question you have to answer. Then it needs to see how this motor works with the vehicle, and how do I integrate this with the vehicle. So that's again another question you have to answer. So on and so forth. So it's not just about the designing, but you have to use a systematic engineering approach in designing and integrating those motors to the vehicle. Okay, coming to the point of how do we come up with the requirements for my electric machine, right? You typically start with a specific set of conditions, specific set of drive cycles. Okay, I'm designing this vehicle mostly for the city uses, something like a hatchback. So you have specific drive cycles that you can refer to. If you have your own drive cycles, you can do the actual road test and create your own drive cycles as well. Once you have those drive cycles from this, you have to include your vehicle dynamics, which includes your rolling resistance, your climbing force, your aerodynamic forces, and your acceleration demands as well. So all this together, that tells you what should be the torque I need to have on the wheel, considering the road friction as well, what kind of a torque and speed I need to have on the wheel. That then goes to the what kind of torque and speed I need to have on the transmission. Of course, the transmission also will have some kind of a losses, and then you also have the transmission ratio that to be considered. And typically you come up with what kind of a torque and speed I need to have on my motor. Now, typically what you generally do while designing the motor is you design it for the lower torque and higher speed, because it is easier to design that way instead of higher torque and lower speed. So you will have always the transmission reduction kind of a transmission in electric vehicles, so that you can design it for a lower torque. It's much easier to design with a smaller size as well, and then increase the torque by using the transmission. But that then gives you an envelope like of operating points across which your electric machine may operate, and that tells you the zone where it will most of the time operate. At the same time, it will give you the envelope, the torque speed envelope that you need to adhere. So there will be the continuous torque, there will be the peak torque, there will be the max speed. That becomes the constants, and that becomes the input to your design. So that is the first point of your design. This becomes the input to my design. So how do you take these inputs and get into the design of the motors, right? Because these specifications tell me what kind of design I want, but what will be that design that needs to become up? You still don't have any drawings of the machines. But many times what happens is you kind of start with some kind of a base designs. Typically, many times you don't start everything from a scratch. You have made some decisions. I want to go with an interior permanent magnet motor. So you already know what kind of topologies those motors will have. So that becomes the base of your design. But on top of that, there are typically back of the envelope or analytical calculations that are done. That's what we call it as a sizing. So these analytical calculations help to kind of narrow down the problem for you. So in terms of what kind of windings I want, what kind of dimensions I want in terms of OD, ID of the motor, those are typically done using analytical based approach, because it's much faster to do that. People have their own analytical tools many times. There are commercial analytical tools as well in the industry, including ANSYS as well. So there are different analytical tools which will help you to size the motor as per your requirement. Now, once you size that motor, you need to, it is a smaller section of your design process. Once you size that motor and you come up with, let's say, hundreds of variations, you use analytical tools to come out with, let us say, 10 designs. Now, once you have those 10 designs, you have to make sure you validate those 10 designs across all the aspects of electric machines. What if there is a fault? What if there is a short circuit? What if there is a sudden locking of the rotor, so on and so forth? Those all different conditions needs to be analyzed, and that's what we call it as advanced magnetic analysis. Now, once the advanced motor is finalized from the electromagnetic point of view, you need to look at the motor from the multiphysics point of view as well, because the motor is not just going to work in electrical domain. It is going to generate the heat. That heat needs to be taken out using the cooling systems. At the same time, it will produce a noise. It may not produce the noise same level of IC engines, but it does produce a high pitch irritating noise. It does produce the frequencies a little higher than the IC engines, which could be irritating to the drivers or the passerbys. So you need to work on those noise as well. Sometimes even increase the noise for some specific conditions, but not general. But you have to look at the motor in terms of multidisciplinary angle. And then finally, you have to also integrate it in the motor in terms of controller. One thing is, if you could design a motor, the best design in that you could come up, which gives 90-95% efficiency, but if you don't design a controller that works together with motor, you will never be able to get a right efficiency out of your motor, and you will significantly suffer in terms of how that motor performs onto the actual system. So you need to make sure it works together with the software control as well. So that's where the control integration comes into picture. So that becomes the overall workflow of how do you evolve your design of the motor from the concept level right up to the integration level. Okay. Now, as I said, you typically you have the motor level requirements. You have the continuous torque requirement, you have peak torque requirement, you have max speed requirement, you have efficiency, you have some laid down guidelines for what kind of efficiency I want to have, what kind of a power factor I am okay to have. Then you have different constraints on your design, right? For example, I have spatial constraints. I don't want the frame size to be higher than this. I don't have length more than this available. I can only mount the vehicle motor in this way, so on and so forth. Those all becomes a spatial constraint. Then there are topological constraints because you have made some decisions before. You have made a decision of going with the interior rotor permanent magnet machines or interior permanent magnet motors. You have also made a decision on how many poles I want to have on the motor. So also selection of poles is also another big exercise, because more poles you have on the motors, you can generate a higher energy or higher torque from it. But increasing the number of poles means you need to produce higher frequencies in your inverter, because let's say if I want to generate a 4000 RPM from a 8-pole machine, if I go with the 16 poles, I have to have the frequencies that generate twice the 8-pole machine. And that puts a significant amount of constraints onto the inverter, amount of switching frequencies that the inverter can support, and what amount of losses you will have in generating those frequencies. That's another factor that becomes significantly challenging. So that's why most of the motors, the permanent magnet synchronous machines that we look at, most of these permanent magnet synchronous machines are typically working with the 8-pole kind of a configuration or less. More than 8 poles, at least in the practical situations, have not been used yet. But of course, there is a lot of work going on there as well. Then again, you have different decisions that you have made. What kind of a topology I want to go with? I want to go with the interior permanent magnet motor, inner rotor permanent magnet machine, or outer rotor, depending on where I'm mounting it, so on and so forth. Those are all becomes a topological constant. Finally, you have different manufacturing constraints as well. You have set of status stamping that only you want to use, let's say you have a specific winding apparatus which needs the slot field to be less than this, so on and so forth, or even the amount of air gap that you can support between the stator and rotor, that also is limited. So those all different constraints are laid down to your traction machine sizing. And traction machine sizing is nothing but an act of precisely balancing all these parameters, because it's every time you play around with one parameter, you kind of have to compromise on something else. And the overall process of traction machine is delicately balancing all these parameters so that you meet your requirement, at the same time you stay within your constants. Be it in terms of the current density that you can have in the windings, or the slot fill, or so on and so forth. So that all needs to be delicately balanced, and that's where I think these analytical tools or the simulation techniques, along with advanced optimization or parametric studies, are significantly helpful in coming with the right sizing of the electrical machines. Now there, as I said, you use analytical tools. There could be Excel based, there could be MATLAB based analytical tools. Typically, these analytical tools use the magnetic circuits principles. They develop the magnetic reluctance circuit of the electric machine and solve it using the linear approximation. You consider the steel to be linear because including non-linear is significantly complex. They work typically with the standard topologies of the motor, something like a very V kind of IPM machines or axial flux machine. There, the analytical techniques typically kind of suffer quite a bit, and you may have to rely with FEA most of the time. So, but they are still very good for the early stage scanning of your design space and cutting down the number of designs from 400, 500 to, let us say, 10 or 15 designs. So analytical techniques are still very, very used. Then you go into the FEA, computational electromagnetics. There you are actually solving the Maxwell's equations in a differential domain, right? You use the finite element algorithms to solve different Maxwell's equations. Of course, you won't solve all 4 of the Maxwell's equations. You will solve the set of Maxwell's equations which are relevant to your problem of the magnetics. So you may solve a specific set of equations using using the FEA solvers that gives you the required. For example, if I'm solving for the motors, I'm solving for the magnetic transient. So I may not solve for the Gauss law, but I'll solve for the other equations. So that kind of decisions are done within the environments, FEA environment, and you do simulations in the FEA environment. Now, once you are in FEA, you kind of do a lot of different studies. You can look at the permanent magnet behavior. Permanent magnet itself has a nonlinear characteristics. They have their demagnetizations because of the stator currents or because of the temperature. So those are all different things you can study. You can study the non-standard kind of characteristics. Let's say I want to have a dual rotor motor. How does it behave? So FEA can handle that. You have complex phenomenon of vector hysteresis that is happening inside the stator and rotor. Your steel is always tracing out the hysteresis loop. Both major and minor loops are there, and those kind of indicate the energy lost in operating the motor. So how do you characterize that? So that is also can be done in FEA. You can use the advanced algorithms to characterize all the different losses in the motor. There are some additional advanced phenomena like magnetostriction and so on and so forth. Those also can be considered using the FEA. So a lot of things that can be done in the machine. So you have to use these techniques to look at how best my motor works in the real operating conditions. Whether there will be a demagnetization, whether there is a lot of losses in certain operating conditions, so on and so forth. So these all different studies are done in FEA domain. Now, once you design the motor, that doesn't stop there, because the motor again needs a controller. And as a motor designer, I have some responsibility. I have to characterize my motor so that I can use these characteristics to develop the motor control. It may be a different team who is developing the motor control, but you still, as a motor designer, you have to look at these parameters and see how best I can improve these parameters so that I can control my motor much better. Of course, there is a MTPA algorithms that are typically applied, maximum torque per ampere in the constant torque region. So you have to make sure that you are extracting maximum torque of every 1 ampere that you add in terms of your stator current. So you have to operate the motor in a precisely operating point that gives the best performance at that particular current value. So those characterization also needs to be done. Again, FEA is used heavily to do that. There are different algorithms. MTPA is not the only one. There is a loss minimization algorithms and so on and so forth. Apart from that, you also need to create these ID IQ maps, LD LQ maps, D axis, Q axis inductances, D axis, Q axis currents, D axis, Q axis voltages, which are very important to implement the motor control, because this becomes the characteristics of the motor when seen from the controller perspective. This is what the controller sees your motor as. So that's where again the characterization becomes important. And when you use the FEA, you also need to you are also expected to extract these characteristics as well from the simulation. So these all different things are typically done in FEA. But another major thing that you have to check is how good this motor works for my operating conditions, right? I need to make sure my continuous torque, my peak torque, my max speed, these are all getting met. But another important factor, now this is what is coming to consideration, right? We talk about many motors getting designed from outside India and getting imported and used into the vehicle. Now, the challenge is the driving conditions in India and driving conditions abroad are not the same. So we generally are talking about localization of the electric machines. How do I design my electric machines that fit to the driving conditions that are in India? Because in outside world, you may be operating in higher speed regions or higher torque regions somewhere here, but in India, you may be operating somewhere here. Now, if your motor is giving maximum efficiency only in this region and lower efficiency in this region, even if your motor claims to be 90-95% efficient, it actually practically will not give that efficiency or will not give that performance in real operating conditions, because it's not giving the right efficiency where I want it. And that's where it becomes very important to lay down your operating points of the motor on top of your top speed characteristics and see where your efficiency regions are and how do I move those efficiency regions closer to the highest density of the operating points I have. So that iterations needs to be drastically done to come up with the design that basically fits right for the required drive conditions, not just on the envelope level design conditions. So you need to make sure that the design is right fit for the driving conditions that it's going to encounter. And again, there is a lot of optimization which is done. There are advanced optimization algorithms that are used to optimize these designs. Even the new set of designs that we are coming up with, synchronous reluctance or PM assisted synchronous reluctance. These all different topologies along with the IPM machines as well use a lot of optimization techniques to achieve that right fit of the motor, to make sure that the whatever the motor we are designing is taking minimum space. At the same time, it is delivering the required highest performance as per my requirement. So that's where the advanced optimization algorithms and robust design comes into picture. Now, as I said, again, it's important that the thermal characteristics are also studied. The motor generates a lot of losses. It generates the eddy losses in the magnets. It generates the core losses in the stator and rotor lamination. It generates a lot of copper losses in the windings. And all these losses will generate a lot of heat. Now, many times the cooling system is on the stator side, but the stator kind of gets cooled, but because of the heat, a lot of heat comes to the rotor, and rotor also gets quite hot. And the rotor typically contains your permanent magnets, which are sensitive to the temperature, because the characteristics of the permanent magnets is dependent on the temperature. If the temperature on the magnets goes too high, they become significantly weaker and may not deliver the required performance. So that's where the temperature dependent study is also important, to make sure that you are maintaining the temperature of the magnets within the envelope. At the same time, you are validating once you calculated was the temperature on the motor, you backfeed into the simulation environment and study what kind of performance deviation I'm seeing. And this is all very easy to do in a simulation environment compared to the physical testing, right? And that's where you have to do all these iterations within a simulation before you actually go into the prototype and testing phase, to make sure that you are kind of maintaining the thermal integrity of your design and taking into account all the possible issues that could result in a real design in a virtual environment itself, before you put it on the motor onto the test bench. One of the big aspect that is getting studied as of now is the automotive NVH. Now, I'm not going, there are many sources of automotive NVH. Some are in electromagnetic nature, some are mechanical. Electromagnetic in nature means that typically your motors, the magnetic interactions that you have in motors. The mechanical noise sources could be your transmission, the gear vine that is coming out of the transmission, the bearing, and so on and so forth. There are also air generated noise, aeroacoustic noise, which could be the wind noises coming because of your mirrors hitting the wind, or the fan or blower, whichever is operating inside the vehicle. And now there are many sources and many areas, but as electric design engineer, you're purely interested in the electromagnetic sources. So when we say electromagnetic sources, it could be coming from your radial interactions of the motor. It could be because of your slot harmonics, or it could be the magnetic imbalance. Now, source of the magnetic imbalance typically is mechanical in nature, because your mountings of the stator and rotor could be misaligned, which generates imbalance forces, whether it is in terms of a static eccentricity or dynamic eccentricity. Those imbalance forces kind of generate a vibration and noise, which can be in audible range and can affect the user. So those also need to be considered. And again, you start off by doing electromagnetic analysis of your machine. You look at what kind of harmonics it is generating. You look at on the motor level itself, what kind of cocking torque it is generating. You try to minimize the cocking torque by changing your design, so on and so forth. But once that is done, you have to study the interaction between the electromagnetics and mechanical, because it may not be generating too many forces at certain frequencies, but it could generate a lot of vibrations if it is falling within the natural frequencies of vibration of that machine. So you, from mechanical point of view, also need to know what is the modes of vibration that electric machine has, what is the natural frequencies it carries, and see if these forces are interacting with any of those modes that will generate the vibrations. And then you can also do the acoustic analysis. You can look at what kind of noise propagation that could happen in the real environment, how much noise it will generate, what kind of decibel level noise you can expect at a certain distance. You can generate your waterfall diagrams and so forth. And even you can create in terms of audible noise as well, see the signal, how it performs. Now, coming to the final section, I'm really sorry. I think we are kind of short on time, but I'll try to cover it within time. So coming to the motor control and system integration, this is again a very important topic, because you, as I said, your design could be extremely good of the motor, but if it is not fitting to the controller and if it is not fitting to the vehicle needs, it will drastically give a bad performance onto the real conditions. So that's where the motor control integration and vehicle integration is very important. Now, typically what you have in a motor controller is basically you sense the motor output through a sensors. Your motor controller reads those outputs, takes the certain decisions based on what control algorithm you have implemented, and it controls the inverter. It controls the switching of the inverter so that it basically increases or reduces the power that is going into the motor, or probably changes the shape of the power that goes into the motor. So that's the overall principle of the closed loop control, right? You study the exact condition where you are at right now. You take some design decisions based on the some kind of a logic that you have implemented, and then make that action through the inverter by controlling the inverter switching, so that the end device gets controlled. So that's the closed loop control that you will typically see in the motor. Now, there are, of course, various techniques. One of them is the field-oriented control, where we talk about the speed control, torque control loops. And many of these control loops will have what we call it as a PID gates, right? You have to have these gates in terms of you have the reference speed, you have measured speed, and you create an error signal from it. And that's typically done through a PID blocks. Same for the torque control as well. You have reference IQ. You want the current IQ, you create an error signal that is again done through a PID block. So these are different PID blocks which needs to be tuned properly so that you meet to the final requirements. And these all tuning the gains of the different controllers is a huge exercise in terms of achieving the right design of the motor or right operating point of the motor. And that's where again a lot of time is spent by the industry. And again the simulation based control tuning or control calibration is model based control calibration is again very new and very impressive area that people are looking into. So there are different ways to do that. You do a electromagnetic simulation, you characterize your motor for overall operation, you create what we call it as equivalent circuit model. Now, typically what happens is when you are doing a control calibration in as a standard practice in industry is done using the fixed parameters. But the problem is your ID and IQ or LD and LQ is not constant. It depends upon what kind of currents you are consuming, what speed you are operating on. These parameters drastically change. So fixed parameter based motor control calibration doesn't work. So that's where the variable parameters needs to be used, and that's what the equivalent circuit models are done. They calibrate your motor for across the different current, different ID, different IQ, different angles, and that then can be fed into your model in loop analysis. Whether you use some kind of a simulation environment like MATLAB Simulink or any other things, or you use the HIL testing directly to integrate. You can feed to that. So this is one example of doing a fixed parameter calibration versus the actual variable parameter calibration, and that integrated into the MATLAB Simulink environment, how there is a drastic variation in terms of the overall performance of the motor and how overall controllability of the motor. So that's what the people industry is looking into right now, is how do we calibrate this motor to the performance of the how do we calibrate the controller to the performance of the motor. Now, another aspect that needs to be looked at is how does this motor work with the vehicle, because motor is not working in isolation. It needs to work together with the vehicle. The vehicle is operating with specific operating conditions, say specific drive cycles, which may or may not be always ideal. But you need to make sure that your motor controller and the vehicle works together perfectly, so that you get a design that fits the right set of operating conditions. So let's say if I have 4 or 5 different designs, I want to make sure which one will give best. I need to put it on a vehicle and see, because ultimately what happens is the motor is the sink of energy, right? It's always driving the energy from the battery. If you don't design your motor properly for an operating condition, it will directly impact the range that your battery offers, and battery is probably the costliest thing on the vehicle. You don't want to waste its energy just like that. And at the same time, you have the challenges of range anxiety and other things that needs to be dealt. So your motor design needs to be on the point to meet your range requirements as well. And that's where the integration of motor onto the vehicle is very important. And there also, again, many techniques are used. You can characterize your motor in FEA domain. You create response surfaces of these characteristics using different tools, different mathematical tools, and generate a meta model of your electric machine. And that meta model can then go and fit into a vehicle level simulators. There are many vehicle simulations, the system simulation environment that are used in the industry to estimate the range of the vehicle. So you can go and add your motor models, which is high fidelity now, because it captures all your non-linearities across the torque speed envelope. It captures all the saturation effects. It captures your losses properly, so on and so forth. So once you create a meta model of your electric machine, and then you can integrate into the vehicle models together with some kind of a driving simulator. You can simulate different drive conditions, be it a semi-urban condition, urban condition. You can even simulate the traffic and signal conditions as well. And you can then see what kind of range you get with the different motors, and what kind of impact it has on the overall range of the vehicle with specific motor. You can change the different motors and see what effect it will have onto the overall performance. So all these things you are doing in a virtual environment before you actually put the vehicle or motor onto the vehicles. That gives an advantage, because now if you have to do on a physical environment, you have to wait until the very end to make sure these all requirements are met. But through the virtualization, you can actually push them earlier into the design cycle and make a more informed decision of your design compared to what you would generally do. So with that, let me stop my presentation. Thanks a lot for listening. Let me stop my sharing and then we can go to the questions. Okay. Please post if you have any specific questions into the Google form that was shared. I see there is only one question as of now, uh, which basically is asking about V2G mode simulation in Simulink. I'm not very conversant with Simulink, but there are there are different modules available in Simulink which helps you to model the driving scenario and things like that. I'll probably refer you to approach the Simulink support in that case and seek the answers from there, because they will be able to provide the right answers to those questions. Let me wait for another minute if there are any further questions. Okay. Okay, I don't see any more questions coming up. Do we want to wait for a couple of more minutes?